Hello everybody, this is Dr. Hussein in Calculus and Linear Algebra. We're still in Module 1, which is Vector Calculus and Matrices. Now this session is about, this week, it's about Vector Integral Calculus, okay, where we are going to discuss the curl vectors, line integral and green theorem, okay. We will follow the same procedure in the last session. Now first of all, you remember we talk about the div. We say that div will give scalar. Now let's see curl, divergence and convergence. Let's see curl of vectors. If we are given a vector A in this way, then the curl of A defined to be curl A, you see, del cross A, just a minute, cross product, which means that we will come up with vector. Yes, correct, we will come up with vector. You see here, this is del, this is A, then curl we will arrange I, J, K, partial over partial X, partial over partial Y, partial over partial Z. This is the del. Then AX, AY, AZ, this is the vector. Now we do our task here. We know how to, as example, if I want to find the previous example in div last week, I took I. Let's take J. J here and here, okay. You see here, this is J. Then this element times this element minus this element times this element. I put them as you can see here. And the same thing for K or Y. You do the same procedure. Now for any one of them, as example here, partial over partial Y for this part, okay. Now minus x squared and z will be dealt as a constant. We only differentiate y, which will be 1, right? So you can see here minus x squared z, I put them multiply by 1. And the same thing for any other one of them. Here example, we differentiate with z. There is no z here, it will go to 0. You see it disappear, nothing here, right? And so on for other elements. At the end I got vector. Now next I will substitute for x, y, z in each one of these parts. Don't forget to use the brackets. We don't want to have mistakes in multiplication, okay. So you simplify and go through it. At the end what we got, vector. So curl vector. This is exercise to you to work on it when you're back home, to enjoy it. I gave you here another vector. I just changed the variables for each element, I, G, K, J, K, and the point here given to you. You go through the same procedure in the previous slide example, and then you will find the curl. I gave you here the answer, okay, just for checking. Now next is to discuss the line integral. Before I start line integral, I would like to have introduction to the topic here, which is related to something you already studied in foundation. If you remember, area and volume, right? We have a standard area, we have a standard volume. As example, square, rectangular, circle, and for volume we have cylinder, pyramid, and so on. You studied this before, trapezium, parallelogram, and so on. In semester 1, level 1, semester 1 mathematical foundation, one of the application of integration is to calculate area and volume, right? We find that as example the integration of the area under the curve, you find the area, and part of it is polar coordinates, which is used to find area and volume. As example here for area, you see this is x-axis, y-axis, and this is the resultant r, okay, with angle theta. Okay, this is the angle theta. What if r change, okay, it's become here, and definitely theta change, so we have ds and d theta, okay, small change happened. This is useful to find the difference when we have a small change in area or volume. You will say, okay, x represented by r cosine theta, because x, as you can see here, opposite, okay, sorry, this is y opposite, x is the adjacent, okay, so it's cosine, and y is r sine theta, okay, and the area, this area, okay, is r dr d theta. This is very easy and direct, as you learn from foundation. Now this is for plane. What if I have cylinder as example? Okay, the same previous idea, just here rather than only x and y, we have z, and z represent the height, another, let me say, dimension came, and let me, rather than using r, I will call it rho. Okay, I will call the radius here rho. Okay, then it will be x equal rho cosine theta, y equal rho sine theta, and z is z. And for area, the small change occurred in area because of a small change in the values of the angles and the magnitude. Then we will write it similar to the previous slide, rho d rho d phi. And if we talk about change in volume, then I multiply by dz. Very easy. This is how we find it. Now, if it is a sphere, the sphere will have another angle rather than only theta. It will be theta plus phi. Then the same previous, let me say, formula in the previous slide, I will add just sine, and cosine here. Okay, and the same thing for area and volume. We have another angle added here in the formula. Now, this is already discussed. It's not my interest now, but just I introduce the topic. The topic is line integral. What is line integral? We want to calculate the area of volume using line integral. Now, line integral, you remember when we do integration for the curve, we find the area. Now, here, small change occur. How I deal with this small change? Have a look. Integration along curve. Let's assume I have curve A to B. You see the curve? Now, I want to find the area with respect to the point, origin point 0. Then this is R. Okay, as a vector. What if small change occur, dr added? Okay, r dr. You see, these are changed. Okay, they don't have the same length. So how can I find it? Okay, have a look how to find it. We have two ways to find. One of them is called scalar field, and the second one vector field, line integral. Now, the first one, which is scalar field, okay, is if v is a scalar, and you want to find the integral along a curve C, then we define it in this way. Integration C here to say along curve. C, it means there is curve. And V with respect to the dr. Dr is something close to the del, but rather than partial, it would call dx, dy, dz with respect to I, j, k respectively. It have many applications in science. Example is the temperature distribution throughout space, pressure distribution in a fluid, spin zero quantum field. So it have many applications. I gave here just example how the energy density change in a fluid as example, and how we can find using line integral. Now, for this method, we have a procedure need to follow. The procedure say, see in this example, it will be clarified. You are given a scalar which is v equal xy square z, and the curve C, this curve defined by x, y, z. X, y, z are function of u, as you can see here. Here 3u, here 2u square, here u to the power 3. He asks you to find the line integral of this scalar across along the curve C at these points A, B. Okay, he gave you 2 points A, B. Here it means x, y, z are 0, 0. Here x3, y2, z1. Okay, now let's see how we solve these type of problems to find the area. Have a look. Now, first of all, I will change everything in the formula. You have formula say integral C, as you can see here, v dr, right? So this v, this dr to be changed into function of u. Even the points A, from A to B, it will be changed into u. How we do this? Have a look. This is v given to you. Now I will substitute x by 3u, y square by 2u square. You see here, z by u to the power 3. Simplify, multiply numbers, 3 by 2 by 1. Okay, here 2 comes square, so it becomes 4 by 3, 12. And u, we have u the base, so we can add the index or the power. I